Gnanam Paramam Dheyam. Knowledge is supreme.
We will continue our study of structure of finite subgroups of a multiplicative group of a field, and today we will prove that these subgroups are cyclic. So what we will prove that if K is any field and G is a subgroup of K cross is a multiplicative group of the field K, and if G is finite, then we want to prove G is cyclic. That means we want to prove that G is generated by one element. That is, in our notation, G is H of Y for some Y. Such a Y may not be unique, and such a Y is also called a generator. Y is called a generator of G, or also called primitive element of G. Primitive element of G. So cyclic group has primitive element, and there may not be unique, there may be many primitive elements. This is what we want to prove. But for the proof of this, we will need some preliminary results on finite groups that I will recall. Some of them I will recall with the SketchUp proofs, and some of them I will recall without proofs. So for example, let us start a typical finite group. For example, we have seen Z modulo M. This is modulo M operations. Congruence modulo M. So there are two operations, plus and dot. And with respect to that, we have seen it is a ring. And whenever we have a ring, we talk about the unit group of the ring. That is usually denoted in this case Zm cross. This means you take the multiplicative monoid Zm dot and take units invertible elements in that monoid. That is obviously a unit, that's obviously subgroup of the multiplicative monoid of Z mod M. This is called group of units. Group of units of Z mod M. And for example, when M is 0, this Z mod M is Z, and therefore Z mod M cross is Z cross, which is only plus minus 1. So it is obviously cyclic of order 2. More generally, if M is positive, remember also when we did the definitions etc. for Z mod M is also same as Z additive group of integers modulo the subgroup generated by M, that is this. So these are the cosets, and they are given by the remainders of when you divide by M. So they are precisely M remainders from 0 to M minus 1. So therefore elements of Z mod M, Zm, also we are denoting this as residues that or equivalence classes. So the notation is this. These are precisely the residues, and they are precisely residues are from 0 to M minus 1. So these are precisely the equivalence classes of 0, 1, 2 up to m minus 1 with the congruence modulo m relation. So when m is positive, the units are precisely Zm cross. These are precisely all those remainders, and we can assume they are from 0 to m minus 1, and the GCD of A and M should be 1. They are co-prime to M. They are precisely the units in Z mod M. And then how many of them are there? That there is a very famous notation for that due to Euler that says that cardinality of Zm cross is precisely phi of M, where this phi is Euler's torsion function. This is Euler's torsion function, which maps any natural number m to phi m, and phi m is by definition cardinality of all the integers, all the natural numbers a 0 less equal to a less than m, and GCD of a and m, the number of co-prime integers, that is the phi of m. So the first thing to note is that because this is a group and order is phi m, if I take any element there, any element will look like any element is a residue, and then if I raise it to the power phi power m, that should be 1 in this in Z mod m. But this is precisely writing this is equivalent to writing that if I raise a to the power phi m, that is congruent to 1 mod m. This is also called Euler's theorem. So this is under the assumption that GCD of A and M is 1. So this is Euler's theorem. For a particular case we have seen earlier, that is the famous Fermat's Little theorem. That says M is P here now. Now any A smaller than P and bigger equal to 1, these are co-prime to P doesn't divide A. So therefore A power P minus 1 is congruent to 1 mod P. Note that in this case phi P is P minus 1 because everybody is co-prime to P smaller than P. So that is the Fermat's Little theorem. Okay. Now I want to recall what is called Chinese remainder theorem. So Chinese remainder theorem, this is about the solutions of simultaneous congruences. Simultaneous solution of a simultaneous congruence relation. So let M1 to Mr be positive integers n plus, which are pairwise relatively prime. Pairwise relatively prime. That simply means if I take any pair Mi and Mj, they don't have any common factor, that is GCD is 1 for all I not equal to j, and let us take M is the product M1 to Mr. Okay, then for every tuple of integers, R tuple A1 to AR of integers, the simultaneous congruences A1 x equal to x congruent to A1 mod M1, x congruent to AR mod MR have a solution in Z. This simply means there exists an integer x, so that x is congruent to A1 mod M1, x is congruent to A2 mod M2, and so on, x is congruent to AR mod MR. Definitely there is a solution. Moreover, a solution is uniquely determined modulo M. Solution may not be unique, but when you go mod M, that's unique solution. So this, in the notation, you can simply reformulate neatly as follows. So reformulation of CRT, Chinese remainder theorem. The canonical ring homomorphism chi bar, which is homomorphism from Z mod M to Z mod M1 cross Z mod MR. This is the product ring, the component wise operations. So any residue here A suffix M, this maps to take that A and take the residues mod M1 etc. mod MR. This is a canonical map, you are just taking the residues. This is an isomorphism of ring. And surjectivity is what the existence of solution, and the injectivity of this map is precisely the uniqueness mod M. So this is also I will keep calling as Chinese remainder theorem. So proof is not very difficult. So proof I am not going to prove this, but I will note down some corollaries. So for example, one corollary, this canonical ring homomorphism, the canonical ring homomorphism chi bar induces an isomorphism of unit groups. That means this chi bar was from Z mod M. So the unit group of, so that notation is chi bar cross, this is Z mod M cross, to obviously the product ring, the units are precisely the units in each component. That means this is the unit group of that product ring. This is an isomorphism, because at the ring level it is isomorphism, so unit level it is an isomorphism. So in particular, the order of this group, that we know it is phi m, which is the order of the group Z mod M cross, but that is same as the order of this group Z mod M1 cross product Z mod MR cross, but this product is obviously the product of the unit groups of Z mod M1 etc. Z mod MR. but obviously this is phi m1 etc. phi mr. So therefore, this means that phi is multiplicative function. That means whenever you have relatively prime integers and when you apply phi to their product, it is the product of the phis. So that was the consequence. That is the property of the Euler's phi function. So further, if I specialize, if I take precisely, if I take m equal to, look at the prime decomposition of m, p1 alpha 1, pr alpha r, where p1 to pr are distinct primes, and alpha 1 to alpha r are positive natural numbers. Then z mod m cross is precisely z mod p1 to the alpha 1 cross z mod pr to the alpha r cross. Therefore, their orders are equal, that is phi m equal to order of this group, that is obviously p1 to the alpha 1 minus 1 times p1 minus 1 and so on, pr to the alpha r minus 1 pr minus 1. So nice formula for phi. Also, we can also formulate the Chinese-Remainder theorem completely in group theoretic terms. So let me do it. So group theoretic formulation of CRT Chinese remainder theorem. So that is the following. Suppose you have G1 to Gr are finite groups, and let us denote G to be the product group with the component wise binary operation, product group. Okay. Then G is cyclic, product group is cyclic. That means it has a primitive element if and only if every factor G1 to Gr are cyclic and their orders are co-prime, and G1 to order of G1 to order of Gr are pairwise relatively prime. So that this again I will not prove, but this depends on this. One can prove this. I will just make one comment. This can be proved easily by using by induction, proof by induction on R, and the following observation about the orders. If G and H are two elements in a group, commuting elements, of positive orders, then order of the product equal to product of the orders if and only if order G and order H are relatively prime. This observation is very simple, very easy to prove. So I leave it for you to check. And now with this, I will prove the theorem I wanted to prove. So that is the theorem. Every finite subgroup G of K cross, where K is a field, is cyclic. This is what we wanted to prove. Okay. K may not be finite field. K may be infinite field also. For example, K equal to C or K equal to R. So, proof. Okay. So, let us look at the order of G. M is the order of G, which is, I will write as a prime decomposition P1 alpha 1, PR alpha R, where these P1 to PR are distinct primes, and alpha 1 to alpha R are positive natural numbers. So, I will call this P1 to the alpha 1 as M1 and P1 to the alpha R as MR. So, M1 to MR are relatively prime now, pairwise. M1 to MR are pairwise relatively prime. So, and now I define Ni to be equal to M by Mi. M is the product, and I am just, this means I am omitting Mi in the product. So, these are integers, these are natural numbers, I is from 1 to R. And it is obvious that the GCD of N1 to Nr is 1. So, that means I can write 1 as a combination of N1 to Nr. So, write 1 equal to B1 N1 etc. BR NR with B1 to BR are integers. And therefore, if I take any x, so for every x in G, therefore x equal to x power 1, which is x power B1 N1 plus BR NR, which is same as, now this is same as x power B1 N1, x power B2 N2, x power BR NR. And these elements I want to call x1, x2 and xr. So, therefore, every element we have written it as a product of R elements x1 to xr. And what about x1 power xi, let us take xi power mi. This is xi is x power bi ni, and then raising it to the power mi, but that is same thing as x power bi, and ni mi is precisely m. So, this is x power m power bi, but this x is an element in a group G whose order is m. Therefore, this x power m is identity. So, this is also identity, and I am denoting identity by 1 because it is a subgroup of K cross where 1 is the identity. So, this is true for every I from 1 to R. This is, if you like, this is equal to 1 by Lagrange's theorem. So, therefore, xi power mi is 1 for all 1 to R. That is what we have checked. But then remember, we are over a field. So now look at this polynomial x power I, fix I from 1 to r, and look at the polynomial x power mi minus 1. This polynomial we know, because it's a polynomial over a field, it has at most m zeros, and I already know that each xi is a 0 of this polynomial. Each x1 to xr is a 0 of this polynomial. It has at most mi zeros, and I know it has so many zeros. If it has less number of zeros, I want to claim that it has exactly mi zeros, because if it has less number of zeros, then G will have, you see here we have proved that every element of G is a product of x1 to xr. So if the number of zeros are of this polynomial is less than mi, then these many components are less. So by cardinality argument, it will have less number, G will have less number of elements. So this polynomial has exactly mi zeros. See, otherwise, if it has less number of zeros, otherwise G has less than m elements. M is m1 to mr elements. So therefore this polynomial exactly has mi zeros. Also, moreover, look at this polynomial x power mi by pi minus 1. This polynomial has at most mi by pi zeros. So therefore, we can find there exists an element yi in G such that yi power mi is 1 and yi power mi by pi is not 1. That is because you see this has to be the 0 of this polynomial. So it is this, and this has more zeros than this. So therefore, I can find an element y which is 0 of this but not 0 of this. That means yi I can find, so that yi power mi is 1 and yi power mi by pi is not 1. But then this means the order of yi, so that is there exists yi in G, I is from 1 to r, such that order of yi is precisely mi, because yi power mi is 1 and yi power pi is not 1. Therefore, order has to be mi, and this is true for every 1 to r. And yi is, so therefore, order of y1 to yr, this product, as earlier noted, that is products of the orders of y1 to order of yr, and this is m1 to mr, which is m, which is order of G. Therefore, this element has to be a generator of G. So that is y1 to yr, y equal to y1 to yr is a generator for G. So G is cyclic. This is what we wanted to prove. So we have proved that all finite subgroups of the multiplicative group of a field is finite, and we will use this fact in the next lecture to construct arbitrary fields of cardinality p power n. So we will continue after the break.